So yeah, as Sean said, we're researching the effects of chiral ionic liquids in synthesizing chiral molecules, and for all of you guys that probably doesn't mean all that much, so we'll go through a brief introduction of the concepts before we start our actual research project.
And to start the concepts, let's begin with chirality. And a chiral molecule has identical composition, but it's present in two forms. The chirality portion occurs at one point due to an asymmetrical carbon. The asymmetrical carbon is represented by a stereocenter. But the stereocenter is due to the surrounding 4 different groups around that one stereocenter, and the 4 groups are the OH, the CH3, the carbon, and the implied hydrogen that is there, and that is what makes it chiral.
So there are 2 different types of chiral molecules, diastereomers and enantiomers. There are diastereomers and enantiomers. The stereocenters, there's always an R and an S. They are both opposites of each other, so these 2 enantiomers both have 2 R and S's. And diastereomers have 2 that are opposite, or at least 1 that's opposite. You can have any number of stereocenters, but 1 has to be opposite, and the rest can be whatever. They can all be the same except for 1, which are both opposite. Also, there is stereospecificity and diastereoselectivity, which are pretty much the same thing, but stereospecificity deals with enantiomers and producing different ratios, or controlling the ratios of enantiomers, and diastereoselectivity is controlling the ratio of diastereomers. The stereospecific mechanism controls the ratios of the 2 molecules produced. And our stereospecific mechanism is an ionic liquid.
And the ionic liquid is a liquid at room temperature, and this is because of its extreme polarity. It has a full positive and a full negative charge, and an average polar molecule has a slightly negative and slightly positive charge. And it is also chiral, as you can see with the asterisks, they show the stereocenters. And we hope this is a stereospecific mechanism because of its chirality and its polarity, so it could possibly orient the enantiomers in such a way that one is favored over the other.
And to measure this, we're going to use a polarimeter. So the polarimeter does is it shoots a beam of polarized light, which already has a reading of 0, through a molecule, and depending on the orientation of the molecule, it will rotate the light in a certain way. So in a 50-50 racemic mixture, which is 50% one enantiomer, 50% another, it will rotate it, or as shown in the picture, which is a 50-50 R2-butanol and S2-butanol. The light will go through this one, rotate in a certain direction, and then go through this one, rotate in the exact opposite direction, so you get a 0 rotation. In ours, we're hoping to get a rotation that's anything but 0, so we know that we got some kind of result.
And as we're going through, we want to make sure the purities of our, we're going to make sure, check the purities of all of our compounds. We're going to use an HNMR through that. And what an HNMR does is it pumps the electromagnetic radiation through the molecule, and it pushes the molecule up and then back down. And once the molecule settles, it'll settle in its desired magnetic field, and this is either up or down. And this in turn gives the peaks that is printed on the NMR sheet. And the sheet shows the integrations, which are the equivalent hydrogens in that one compound, in that one carbon group, and splitting it is the amount of hydrogens in the groups surrounding. Therefore, when we look at this NMR, the blue hydrogen shows a triplet peak, and that is due to the 2 green hydrogens that are surrounding it, but it is the neighbors plus 1, and so this shows us a triplet peak.
So to begin our synthesis of the ionic liquid, we got a conical flask full of toluene, reduced it to 5 degrees Celsius, added menthol and dissolved that, and then added some paraformaldehyde, and bubbled hydrochloric HCl gas through that for 3 hours. And to get the hydrochloric gas, we did the reaction sulfuric acid and NaCl, which is table salt, and we bubbled that for 3 hours and got 4-methylmenthol ether, which is the beginning of the ionic liquid. That's a completely new molecule unique to this project.
And here are NMRs. On the right, on the left, your left, there's the blue NMR is our mentor Sean's NMR. It's his pure chloromethyl ether, and to the right is our pure chloromethyl ether. And as you can see, it has some slight variation, but the biggest variation is that around 2.4 in ours, there's a larger peak, really large, and we suspect that it is a leftover toluene compound that could change, would vary our results versus his.
So next in our reaction, we took the chloromethyl ether and mixed it with 1 butyl-imidazole to try and displace the chlorine. And through that reaction, we got an imidazolium salt. And that in itself was a salt, but it wasn't an ionic liquid because it was solid room temperature. So in order to make it an ionic liquid, we put another anion group in to displace that, or to replace that chlorine. The anion groups that we used were NADF4, which is sodium tetrafluoroborate, and NaCF3COO, which is sodium trifluoroacetate. They replaced the chlorine, and we got a much bigger molecule which did not solidify at room temperature.
As we were synthesizing the chiral molecule, we used the 1-phenyl ethanol to be used as a control for when the ionic liquid is used for the same synthesis. And when synthesizing the 1-phenyl ethanol, we used sodium borohydride, mixed it with ethanol until it was all together. And then we added the acetophenone for 4 minutes, and then HCl so that it would separate during the boil.
We also did our ionic liquid reaction where we made the 1-phenyl ethanol racemic mixture, which we hope wasn't going to be racemic. We replaced the ethanol with the ionic liquid, and to get the 1-phenyl ethanol out of the solutions, both of them, we used a separatory funnel. In this funnel we had ether and water. The 1-phenyl ethanol was soluble in the ether, and everything else in the solution was soluble in the water. So we collected the ether in the first reaction, and we boiled that off and had the 1-phenyl ethanol pure. And in our ionic liquid reaction, we were supposed to have 3 layers because the ionic liquid is not soluble in either water or ether. And instead we had 2 layers, which indicated that something strange happened. So we asked our mentor, Sean. He said that the ionic liquid had broken. And we're not sure exactly what it broke into, but it probably occurred right around that area. And so that was soluble also in ether. So we need to get both the 1-phenyl ethanol and those 2 out of the solution, and then get the 1-phenyl ethanol out of those 2. So we used chromatography.
And we started at a smaller scale using TLC plates, and that is thin layer chromatography. And what a TLC plate is a glass plate with silica gel on top of it. And the silica gel, once a UV light is placed over it, it'll glow a brightest yellow as shown there. And the solution on top of it will dim the light so we can differentiate exactly where it would be. And we had to try different solvent systems that we could use so that we could figure the best situation that would help figure it out. And we started with the 60-40 mixture, and it obviously just showed that it just smeared the spots more. And then we tried the 90-10 hexane ethyl acetate solution, and it showed to separate them out better and give us the spots clearer. And we wanted the top 2 spots of the 90-10 that was shown, and that's how we figured what these flasks we should fill.
So then we move on to column chromatography, which is shown in this picture. We use silica gel, which is the same stuff as here, but in a much larger scale. The solvent system was also the same, 90-10 hexane ethyl acetate. And we ran that through the column first, did silica gel. And once that got about level with the silica gel, we added our compound. And then we kept on adding more solvent and collecting out at the bottom of the column. And those had the different compounds separated. As seen in this picture. This is run by our classes 1 through 6. We used 15 milliliter increments. So this, or about 2 through 6 had the first dot. So we boiled off the ether. We boiled off the ether and we had one compound in E flasks 2 through 6. And also in 9 through 12 we had this dot separated. And that's not pictured there. So then we NMR'd both of those and we got this.
So on the upper left we had the first 2 through 6, and the upper right we had like the later 9 through 12. And at the bottom that is a published version of a 1-phenylethanol, and that's what we were trying to get from the Ionic liquid. And E flask 2 through 6 didn't quite look exactly the same, and 9 through 12 showed to look a lot.
We have one data point of 0.008. We only used the BF4 ionic liquid as well. We didn't use the CF3COO because as I said, we had time constraints. Yeah, so here's our picture citations, our works cited page, and our acknowledgements.
So we would definitely like to thank UNC for accommodating all of our room and board, and then SSI for the acceptance and the gratitude. And then I personally like to thank the Adolf Kruger Foundation and the Bacon Family Foundation for sponsoring my room and board and research.
I would like to thank the Morse family and the Edward Madigan Foundation for sponsoring me in both room and board and research. We'd like to thank Sean Johnson for mentoring us and just sort of teaching us all about this because we had no idea. Sean Hoskins for his class and for everything he did as an advisor, grading our papers, helping us with this presentation, and especially with our poster.
Okay, and we would like to thank Ghost and Tales for always being there, strong supporters, and all the FSI staff for also being strong supporters through all of our research and our classes and just all the trips that we go on. And, yeah.
Are there any questions?
Do you happen to know why the Ionic liquid broke?
We're not sure, or not all that